Hello, good greetings, guys. I don't want to say good morning, good afternoon, or good evening because I don't know where you are. But anyway, greetings, and we are continuing with our DIT 230, BIT 140, which is data communications as well as networking. Today, our Unit 8 is focusing on LAN wiring as well as physical topology and interface hardware. By LAN wiring, we are looking at local area network wiring, the types of wires that are found or the cables that are used in a local area network. Physical topology, remember we said for topologies, you have logical topologies, that is how the data moves, as well as physical topologies showing you how the physical layout of a network is. We also have interface hardware, that is the hardware that is found or that is used to connect computers to the network. It can be a computer to a LAN cable or any other device that is used to connect devices such as computers to the network. LANs come in various speeds. If you've noticed, by now we have speeds as high as 1 gigabits per second. That's how fast some LANs are, okay? Some are 1 gigabits per second. So they're able to move data as big as 1 GB per second. Okay, that's a huge data. If you are downloading a movie and imagine you have a network that is able to allow you to download at 1 GB per second, which means if a movie is 700 MB, within a second, you should have downloaded it. So in most countries, that's what is happening. In countries like Zambia, we are not yet there. But with all things being equal, I'm sure we shall get there one day, okay? We are also saying some Ethernets operate at 1 GB, which I've said, and the conventional CPU. The CPUs in most laptops and computers, mostly the highest at the moment is 3 gigahertz per second. So even if it can execute one instruction in each clock cycle, a CPU running at 3 gigahertz cannot handle data as fast as 1 GB per second, which is arriving from an Ethernet network. This is because instructions required for each bit may be too much for this CPU to handle. The difference between the CPU speed and the network speed is fundamentally a problem, okay? Networks are designed to operate at the highest rate the hardware can support. So if the hardware that is being used in a network can support maybe up to 3 Mbps, which means even if you're connected to whichever wire, you can only be able to transmit at that speed. So the hardware that is used in your network can determine the speed that your network can handle. Network hardware. A computer has a CPU, and the CPU does not process the individual bits on a network. There's a special purpose hardware that connects a computer to a network, and it handles all the details of packets that are being processed. If you've noticed any computer or any laptop, there's that point where you connect a cable for your network. This is a special hardware we are looking at, which helps us to connect the computer to the network. This special hardware is what we call a network card or a network interface card. You'll see a figure later on which illustrates how the network interface card might be positioned in a PC, like a desktop. As well as you'll see another figure that illustrates the connection on the back of a PC. So obviously on new laptops and computers, network interface cards are mostly built in. It's not something that you can remove and plug back. These usually come already mounted on the motherboard. Most network interface cards contain what is known as the direct memory access or DMA circuitry. This DMA circuitry allows the network interface card to operate independently from the CPU, which is the network interface card can process its own data which is sending or receiving without the use of the CPU. The network interface card can transmit as well as receive bits without using the CPU, just like I'm from explaining. Cheap network interface cards do not support DMA, which means they rely on the CPU to process their data. To receive a packet, the CPU allocates buffer space in memory. I hope you've done that in architecture yet. So that I don't need to explain what buffer space in memory is. So the CPU allocates buffer space in memory for the network interface card to be able to process data. This is in a scenario whereby the network interface card doesn't have direct memory access. Okay, after it allocates memory, it then instructs the network interface card to read the next incoming packet into buffer. So these packets will be pushed into the buffer memory. After the CPU has acted on it, it will be moved out. Another packet can be moved in, just like that, until all the packets are received or sent. Okay. So this is, if you've seen this figure we are just basically showing you how network interface card slots are in a desktop. So when you open a desktop, you find that there are those slots. One of the slots is a socket for interface cards on the motherboard. So there are other slots for things like VGA, but you should bear in mind that there is one slot that is always reserved for a network interface card. This is what you're seeing from the inside. When you start looking at the box, like you've closed it, when you look at the opening, you find that there is that opening there. That's where we connect, even in our labs, you connect that cable, the internet cable. So this is just a diagram of how that may look. The connection between a network interface card and the network. So the type of connection that is used between a network interface card and a network depends on the network topology. The type of connection used between a network interface card and the network depends on the network topology. So in some technologies, the network interface card contains most of the necessary hardware. That is, it attaches directly to the media using a single cable or optical fiber. In many other technologies, the network interface card does not contain all the electronic circuitry needed to attach directly to a network. So in this instance, the network interface card cable attaches to an additional circuitry which attaches to a network. Exact details of the connection between a network interface card and the network are not determined by the technology. Why? A given network technology can support multiple wiring schemes. We'll get to what we've just looked at soon. Let me just even start a PowerPoint so that if I need to demonstrate something, I'm demonstrating from there so that you're able to follow. Okay, we're saying a blank presentation. Okay, can we erase that? Okay. Okay. So in case we need to do some, in case I need to do some explanations, I'll need to use that PowerPoint. Okay. So just like we have generation, 3G, 5G, 4G, even in terms of cabling, we have generations. So cables have evolved from the time network started, up to now. So the evolution of networks. Let me do this. Am I able to do what I want? Let's say. Okay, I want a pen. So we are saying the evolution of networks Okay, we'll get to it. So this evolution of network, we are saying the original thick Ethernet wiring. So the cables, like the cables that you've been seeing now in our computer labs, wherever you've been, they came from somewhere. So there has been an evolution. So the original cabling that was used in a network was called original thick Ethernet wiring. Original thick Ethernet wiring. The original thick Ethernet wiring scheme was informally called thick wire Ethernet because the medium was of a large coaxial cable. So thicknet is the name that they gave it. And thicknet used to use a large coaxial cable. The hardware of thicknet was divided into two major parts. One, a circuitry that handled the digital aspects of communication, including error detection through CRC, as well as address recognition. So we are saying thicknet used a large coaxial cable. That's why even the network was referred to as thicknet. If you compared with the cables that we use now, the cables are smaller in size. But imagine if you have this network that you are using coaxial cable. I'm sure the trunking, those boxes where cables pass in let's say in a lab or in a network, they would be so huge. Imagine you have 500 computers and you're passing 500 coaxial cables. That would really take up much of your space. So with thick Ethernet wiring, they used to use coaxial cable, and we are saying they used to refer to it as a thicknet. Okay, before I go there, let me just go to the top. So the hardware of thicknet was divided into two major parts, like I've said. There was one, a circuitry that handled the digital aspects of communication, including error detection and also address recognition. We also had this transceiver, which was an analog hardware that handled signals such as detect a carrier, which is simply detecting a signal, converting bits into appropriate voltage for transmission, as well as converting incoming signals to bits. This transceiver was usually placed at a remote site or a far distant space than where the computer is. For example, in an office building, transceivers might attach to an Ethernet, okay? And then the cable connecting the network interface card to a transceiver was called or is called an attachment unit interface, AUI. So the connection that is between the cable that you are using in thicknet and the network interface card, the connection is called AUI connector or AUI cable. Okay, I'll get to that. I'll show you what connector we are looking at. So I've just said AUI connector. So thick Ethernet used a connector called AUI connector. You should take note of that because I may ask you to say, give me the 3 generations of Ethernet wiring with each state maybe the connector that was used. So in thicknet, the connector that was used was the AUI connector. Okay, so this is thicknet. This is an example of a thicknet. So like I was saying, you have transceivers there. You've seen those transceivers. This is like a bus network. This is like a bus network. So in this bus network, we have this transceiver. So between the common media and the computer, there was a transceiver. And then from a transceiver, this is a AUI cable, which connects to a network interface card there. So this network interface card had a connector, which we refer to as a AUI connector, where the cable and the interface card are connecting. That's called an AUI connector. So in thick Ethernet, the type of cable that was being used was coaxial. This time, the cable that connects from the transceiver to the network interface card is called the AUI cable, and then the actual connector that is used in the network interface card is called the AUI interface or AUI connector. Okay. And then at the far end here, we have seen they've terminated the cable. We'll look at why the cable is terminated at the far end there. Okay. So each end of the cable must be terminated or must have some terminator like we have seen there. Why is that so? It's so because once a signal reaches the terminator, the signal gets to be discarded. Let's say machine A has sent something to machine B. Remember we said on a bus network, when one computer sends to another, it will send to all the other computers on this network, okay? So when machine A sends to machine B, whatever machine A has sent will also reach machine C. So after machine C, it can also be sent to the far end there. But what happens in this scenario is, if something is sent up to there, then it can still bounce back on the network and still send back to even the owner that sent this message. So with terminators at the end, they are used so that when a signal reaches at the end of the cable, it gets discarded so that it doesn't get to be sent back to the owner or to the sender. I may ask such questions. I only hope I'll get the correct answers that I expect. Termination is essential for correct operation of a network because the end of an determined cable reflects signals just like mirrors reflect light. When the reflected signal reaches the sending station, it will confuse this as interference. So if it reaches the far end and then the signal gets to be sent back, this may feel as if there is some interference, and yet there is no interference. Therefore, the sender assumes that the interface is caused by another station, which is not true. Okay? If that is done, it's possible that the Ethernet may evoke the back-off algorithm normally used to handle collision. We looked at this when we were looking at carrier sense with multiple access. So if you are blank, you can still go back to that handout. It should be handout 6, then you'll find what the back-off algorithm does. Connection multiplexing. Ethernet specifies a minimum distance separation between two transceivers, okay? Individual transceivers must be placed along the Ethernet cable. If you had seen, individual transceivers are placed for each computer along the Ethernet cable in a network. To solve the problem of computers in a single room, trying to connect to a network, they use a connection multiplexer. I'm sure by now you know what a multiplexer does. So this multiplexer must be used. A connection multiplexer allows multiple computers to attach to a single transceiver. So there may be possibilities where you have this transceiver there, one transceiver, and a multiplexer. So all computers are connected to a multiplexer, and then the multiplexer is connected to a transceiver. For example, if this is one office, because in one office it wouldn't make sense to have a lot of transceivers. So all you do is have one transceiver which is connected to a multiplexer, and then the computers are connected to a multiplexer. Apart from thick Ethernet, we had the second generation of cables, which was called thin Ethernet. So thin Ethernet was the second generation of Ethernet wiring, it used a thinner and more flexible coaxial cable than the original thick wiring. This was formerly named as thin wire Ethernet and informally known as thicknet. So thick Ethernet wiring was, if you remember, informally they refer to it as the thicknet. And the second generation, which is thin Ethernet, is informally referred to as thinnet. So thinnet differs from thicknet in some way. Why? Thicknet generally costs less than thickness to install and to operate. Why? These are the reasons. Why? Because the hardware that performs the transceiver function is built into the network interface card. So no external transceivers are needed. So if I ask you the difference between the network, how thicknet is done and how thinnet is done, you find that in thicknet, the transceivers are separate from the network interface card there. But in thinnet, the transceivers are actually built into the network card. So you don't see the network the way it was there, where you have a straight line and then you have transceivers for each machine. In this scenario, the transceivers are actually built into the actual network interface card. So one difference is because the hardware that performs the transceiver function is built into the network interface card. No external transceivers are needed. Again, thinnet does not use an AUI cable. This cable that connects between a computer and a transceiver. Thinnet has eliminated that. Why? Because the transceiver is actually built into the network card. So it attaches directly to the back of the computer using a BNC connector. So I said for thick Ethernet, the type of connector is called AUI connector. But for thin Ethernet, the type of connector that is used where you connect the cable to the computer is called the BNC connector. This BNC connector is just like the one that we see in our homes. DSTV, that type of connector, or GoTV, the connector that we use, that connector is called the BNC connector. So computers in the second generation used to use such kind of connectors. Right now, you are using what we call RJ45, but then the type of connector that was there was called a BNC connector. Okay. We have a third generation of cables or wires. The third generation of cables which we are currently using in today's Ethernet is called twisted pair. This is where you find things like UTP. So a third generation of Ethernet, or today's widely used technology, is referred to as twisted pair Ethernet. This differs dramatically from both thick as well as thinnet. It does not use coaxial cables, but it uses twisted pair cable. An electronic device serves as the center of the network. Okay. This is known as Ethernet hub. So you'll find that in a twisted pair Ethernet, there is a device that is introduced. This device serves as the center of the network. And when we are looking at topologies, we also mentioned to say the star network, where the twisted pair is mostly built, comes with an equipment in the middle. And this equipment in modern day technology can be a switch or can be a hub. Okay. So the connection uses UTP wiring with a RJ45 connector. So twisted pair cable uses a connector called RJ45. If you've connected your computer in a lab with that network card, with that network cable, that connector that you see is what we call an RJ45 connector. We have a AUI connector for thick Ethernet. We have a BNC connector for thinnet. For twisted pair cable, the type of connector that is used is called RJ45. Let's get to master all these guys. So what we are saying is, if you have to depict a network that is formed using UTP, there is usually a hub or a switch where each computer connects. Each computer connects to this hub or a switch. And then the point where the cable coming from the switch or from the hub to the computer connects has a connector, which is RJ45. RJ45, just like the BNC connector as well, it is embedded in the network interface card. Okay. Electronic components in a hub emulate a physical cable, making the entire system operate like a conventional Ethernet. For example, a computer attached to a hub must have an Ethernet address. A computer must use carrier sense multiple access with collision detection to access the network, as well as the standard Ethernet frame format. Okay. There you can just read on. This is just for information. So software does not distinguish between thicknet, thinnet, as well as twisted pair. So no software will be able to distinguish if you're using thicknet, thinnet, or twisted pair cable. The network interface card handles the details and hides any differences. So you may find that another network somewhere, they are still using thinnet or thicknet, but your computer won't know if you're using thinnet or thicknet. Those things are handled by the network interface card. We have advantages as well as disadvantages of these wiring schemes. So each wiring scheme has advantages as well as disadvantages. Wiring that uses a separate transceiver per connection allows the computer to be changed without disrupting the network. Whereas thin Ethernet became popular because it costs less per connection than the original thick Ethernet. Twisted pair cable as well, this twisted pair wiring is now popular because it costs less per connection than thinnet. So as the generations were going, the costs as well tend to be reducing. So of course, our statements are generalizations. Actual costs are not always easy to compare. The total cost always depends on these items here. You can just read on them. We won't talk much about that. Okay. The topology paradox. Okay. This, just read on it. I'm not likely to ask you anything, but just read for the sake of reading. Okay. To make it possible to change. Okay. This as well, I don't expect anything out of there, but just read on your own. I may not ask anything out of that. But last but not least, what I want you to see is the connectors. So second generation of Ethernet wiring are the BNC connector, just like the one you have on your decoder, where you put that coaxial cable. AUI connector, this is how it looked like, just like the way where you connect your VGA cable. This is how it looks like. RJ45, the one we are familiar with in most computer labs on your laptop, that connector that is there, that's called an RJ45. The stuff that comes down there, I don't expect any questions to come from there, but just read through for your understanding. This has been our unit 8. In case you have any questions, you can always drop them on the platform. That's the WhatsApp platform. Or you can as well just send them directly to me. Then I should be able to advise. Be on the lookout for the next video, which is unit 8. And like I said, Thursday, we should expect our test 2. So on Thursday, I expect you people to come through so that we should be able to just write that test.